Let us talk about Fresnel by Prism. Fresnel by Prism, or otherwise we can refer it in terms of Fresnel's mirrors as well. Now let us talk about this one now in detail. Actually, Fresnel used a biprism to show the interference phenomenon. So basically, Fresnel is the name of the scientist, and Fresnel used a biprism to show the interference phenomenon. Now for this one he considered a biprism. Okay, here the biprism which is indicated with ABC consists of two acute angle prisms. It consists of ABC consists of two acute angle prisms placed base to base. Actually we are saying two acute angle prisms, but it is normally, but actually it is a single prism of obtuse angle of about 179 degrees respectively. Actually we are calling it as two acute angle prisms. It is basically, as the base is, from the base is what we are locating that prism base to base, but actually it is done on a single prism with respect to an obtuse angle of about 179 degrees. As we are stating it in terms of the acute angle prisms, so the angles are obviously 30 degrees on the either side of that particular prism. So we are saying that the acute angle we are denoting it with alpha, that will show it in the diagram. The acute angle alpha is about 30 degrees on both sides of the prism. Next, so coming to the construction part, this is entirely how you are constructing a Fresnel's biprism. We are saying it is used, a biprism is basically consisting of two acute angle prisms placed base to base. Actually it is a single prism of an obtuse angle of about 179 degrees, but we are making two acute angle prisms from base of that particular prism, and we are saying that the acute angle prism angle is about 30 degrees on both sides of the prism. Next, the prism is placed with its refracting edge, or otherwise the refracting surface, parallel to the source S. So S is the chief source of light what we are using here. So it parallel to that, we are making the refracting surface of that particular prism almost parallel to the monochroma, that is your source of light S. Next, here now in doing so, by placing it normal to S, the surface, or the what you call the ray, or otherwise we can refer it as the SA, is normal to base of the prism. SA is normal to the base of the prism ABC. Base of the prism here is nothing but BC. Okay, BC is supposed to be the base of the prism. So SA is drawn normal to the base of the prism BC. Now this is the working phenomenon or the construction part regarding the Fresnel's biprism. Now let us construct that particular figure over here. Now in this we are talking about Fresnel's biprism. Here we have the prism. This is prism ABC. Okay, this is A, this is B, this is C. Okay, now here these are the acute angles which we are writing it as alpha. Okay, now from here okay, now we said it is drawn with reference to a single prism, right? Now let us construct such case of a thing over here. So this is from the source S. Okay, now okay, this is S, this is your source of light. This source SA, so this one is SA, what we are talking about, the point. It is normal to the base BC, the prism. This is obviously an obtuse angle triangle of about 179 degrees. Okay, now this is about the Fresnel's biprism, the initial part of the Fresnel's biprism, where we are allocating the angles with respect to acute angle as well as the obtuse angle, and SA being normal to the base BC. Now in the second part of our this thing, so here what we do here is, if this source of light is allowed to fall on the upper portion of the prism as well as the lower portion of the film, what will happen to the direction of the light ray? So how it gets deviated onto the respective paths is what we are going to see now. Now along these particular positions we are framing it as such. This is for the upper portion. This is from the lower portion. Let me extend this line over here. Okay. One small portion. Let us consider this as capital A, this as B. Okay. This A and B will act as the coherent sources. Okay. Now the distance between A and B is taken as small d. Okay. Now corresponding to these sources, this is your chief source parallel to BC is what we are making up over here in this case. I am extending this line. Let me finish the diagram first. So from the figure itself we have done that SA is the point normal to BC. Okay. The next case is, now we have some portions of light getting bent in terms of the upper as well as the downwards of the prism. Now let us based on these respective assumptions, so let us try to analyze the things over here. In the first case, what we have seen, SA is normal to BC, up to that point is what we have confirmed. In the second sense, from the diagram we have here, when light falls from S, that is from source S, on the lower portion of the prism, then so we are talking about S falling on the lower portion of the prism here, this particular portion of the prism, then the light ray is bent upwards, it bends upwards and appears to come from the virtual source B. So here, so light is falling on the lower portion of the prism. when this is the view, then it appears that when it is appearing on that, it appears that the image is bending towards the upward direction. So this is what we can see here. So this is the upward direction. Let me mark it with one more sketch here. So this is bending towards the upper ray. So this is the upper ray what we are seeing here. Okay. Now, how does it appear? Once it is falling, but what is that we are transforming from here? Here it is assumed that it is coming from the virtual source B here. So here B is acting as the virtual source. So it appears to be coming from in that when the source of light is falling on the lower portion of the prism. Similarly, in the next case. So what is the next case here? In the next case, we say that when light falls on the upper portion of the prism, then the light ray is bent downwards and appears to come from virtual source A. Okay, so let me show it in the diagram now. Here what is that we are showing? This source of light S. Okay, this is falling on the upper surface of the prism. So this is the upper surface of the prism. So when it is falling, so when it is falling on the upper portion of that, it is tending to bend here. So this is how we are indicating this. So this is bending towards the lower portion of the, it is bending towards the downward portion. So this is how we are making the light ray bending. So it resembles that this particular one is coming from the virtual source A here. So this is from the virtual source. So as per the diagram we are getting, and it is assumed that it is coming from that portion, but actually it is not happening. Here S is the light which is falling. These are the other two virtual sources of light. A and B are considered as the two virtual sources of the actual source of light. So here we say that, so when light from S falls on the lower portion of the prism, then the light ray is bent upwards and appears to come from the virtual source B. Similarly, when the light falls on the upper portion of the prism, then the light ray is bent towards and appears to come from virtual source A and A. Then similarly, here from these two respective considerations, we can say that here, therefore, from the previous considerations, we see that both A and B are acting as two virtual sources. They are acting as the two virtual sources. These virtual sources are almost two virtual sources which are coherent in nature. Okay. Now, in the similar case, let us suppose that the distance between this, already we have done when constructing the diagram. We suppose that the distance between the two coherent sources, between the sources A and B, small d. So that we are confirming from the figure itself. So here the distance between A and B is taken as small d. Now when we do that, if a screen is supposed to be placed, at point C, then interference fringes interference fringes of equal width are produced between E and F. Okay. So here we are what we are trying to say over here is, if this C is supposed to be placed at the screen. So this is your screen here. This is your screen. Okay. This is what the slit. You can call it as the slit. Okay. Now when C is placed, then you can see that what is that we are seeing? At C, interference of equal width are produced between E and F. So what are these? This is what we take up the fringe width. So these are the fringes of equal width. So let me show it in a proper sketch here. So these are the fringes between E and F. So if equal widths, if C is the point at which the screen is supposed to be kept, then we are going to have between E and F is what we are able to see the pattern here. So these are the points. So this is the complete width, but between E and F is what we are trying to say. So the point between E and F, between E and F. Okay, so the one which are crossed over here, they are out of the content. Out of content in the sense, so they are beyond that point of imagination where they are out of. That is, they are not a part of our this thing, where we say that beyond that particular respective point, where we call them as indistinct. We have screen, if at all a particular screen is placed at C, interference fringes of equal width are produced between E and F. So if the screen is placed at C, we are going to have a fringe of equal width. But if it is placed beyond C, so beyond C, if screen is placed, then if the screen is placed, then beyond E and F the fringes are supposed to be formed. So here we say that if a screen is placed at C, interference fringes of equal width are produced between E and F. Now beyond C, if the screen is supposed to be placed, then so beyond C we have unequal widths of fringes being formed, but it is out of E and F. That is what we write it over here. So we say that beyond E and F, so if the screen is placed beyond E and F, larger width of fringes are produced. Okay, so this is if the screen is supposed to be placed at C, so this is beyond E and F, larger width of fringes are supposed to be produced. Okay, now so this is for the unmatched fringes is what we say. Now, so in order, how can we alter the light rays? So the light rays can be altered by making use of the slit. So this is the actual slit, M and N. The purpose of M and N is that we can limit the rays. So to limit the rays, we are providing it with a slit which is Mn. Okay, so here Mn is a stop. So Mn is a stop to limit the rays. Okay, next, coming to the next point. So here to observe the fringes, what is that we require? To observe the fringes, the screen is replaced by an eyepiece or a low power microscope. for a low power microscope. And fringes are seen in the field of. Now we are seeing about this one. Now here C is placed at this, and it is also provided with an eyepiece here. So this is the eyepiece. If a screen is not placed, then just by replacing this screen with an eyepiece, we can see the fringes over here with this particular eyepiece. Adjusting the screens in such a way that the width of those fringes can be seen. Or otherwise, or instead of an eyepiece, you can use a microscope. A microscope of low power can also be replaced with a screen. So there are two certain cases of things which we can replace the screen. For the screen, we can find out the fringe widths by obtaining those fringes directly. That is, alternate dark and bright fringes can be seen on the screen. And if the screen is not allotted, then we can make use of the purpose by making use of an eyepiece so that we can view that fringes, as well as a low power microscope is also used to see the fringes and the fringe width respectively. So that is what we are confirming from this respective point. Then next, coming to the next point over here. Now, if the point C is at the principal focus, if the point C is at the principal focus, then we can view through the eyepiece and in terms of the field of view. So we can say that the principal focus of the eyepiece, if the point C is at the principal focus of the eyepiece, then the fringes are observed. Then the fringes are observed in the field of view. In the field of view. So this is for the adjustments made with respect to the eyepiece, whether it is at the point C or at the principal focus. Then obviously we see that if the point C is supposed to be equidistant from the two sources, that is, C is supposed to be equidistant from A and B, then at that particular point, if they are equidistant from A and B, then a point on the screen noted at the brighter region, we can calculate the fringe width accordingly. So let me write down the formula. Now if C is supposed to be equidistant from A and B, so that is the condition. So we say that here the point C is equidistant, means if it is placed at equal distances from A and B. That is what we mean by the word equidistant. The point C is equidistant from two sources A and B. Then what is happening? It is equidistant from A and B. Then the point C has maximum intensity if they are equidistantly placed. Now, so it has maximum intensity, that is at the center itself we have the maximum amount of brightness. Now at that particular point, the width of, we already said that there are alternate bright and dark fringes being formed around that particular point C. So to calculate the width of that particular fringe, the width of the fringe at any point, the width of the fringe at any point on the bright fringe on the screen, at the center of the screen rather, at any point on the center of the bright fringe on the screen is given by beta is equal to lambda d by small d. So this is for the fringe width is what we are calculating. Fringe width beta is equal to lambda d by small d. This is for what? at the center of the bright fringe. Okay, that is for the condition of the fringe width. Okay, next, simultaneously coming to the next point over here. At any point on the screen, at any point on the screen, at any point on the screen, at any point on the screen will be at the center of bright fringe if its distance from C is n lambda d by d, where n is equal to 0, 1, 2, 3 and so on, etc. So, moreover, at any point on the screen will be at the center of the bright fringe if its distance from C is n lambda d by d, when n is equal to 0, 1, 2, 3 and so on, etc. Then, so this is the condition. So, at any point on the screen at the center of the bright fringe, then it is given by n lambda d by d. Obviously, at any point on the screen will be at the center of dark fringe if its distance from C is, in place of n, we do it with 2n plus 1 into lambda d by d, where n is equal to 0, 1, 2, 3 and so on, etc. So this is the condition. So at any point on the screen, so what we mean by these respective sentences is that first, the width of the screen, the width of the fringe, or we can say that for a dark fringe, that is exactly at the center, then beta is equal to lambda b by d at the center of the, so this is with respect to the center of dark or bright fringe on the screen. If you want to identify any point of a fringe which is obviously on the screen, then we calculate it as beta is equal to lambda d by d. But if the same is the case for at any point on the screen at the center of the bright fringe, we are talking about alternate dark and bright fringe, and you are selecting at the center of the bright fringe, then the distance from C is taken as n lambda d by d, and n is 0, 1, 2, 3, etc. At any point on the screen, if there is at a point on the dark fringe, then its distance from C is given by 2n plus 1 into lambda d by d, and when n is equal to 0, 1, 2, 3, etc. This is how we can determine the points with respect to the Fresnel Bi prism. Moreover, within a given limit between E and F is what we have seen it from the diagram. So the fringe width can be calculated. That is, alternate dark and bright bands around that particular point will happen. So if we are obviously taking with respect to the dark fringe, there is one condition, that is n lambda d by d. With respect to the dark fringe, this is 2n plus 1 into lambda d by d. So these two respective points is what we can consider for a Fresnel Bi prism. So this is how we finish it off for the Fresnel Bi prism.